For page 25, it involves change of variables, but I also have this standing rule where if you have a definite integral, you can use your calculator if it's on a test. All right, so I'm not going to make you use a by hand approach to evaluate a definite integral. There's a time and a place for that. I don't think this is it. All right, but I will walk you through the technique, and who's to say Calc 3 differential equations course you might need to do it. Sometimes the bounds are variable, in which case you definitely need to do it. So you want to learn the skill. But if it's a definite integral with numerical bounds, I'm not going to ask you to do it using a by hand approach. All right. So let's let u be equal to x cubed plus 8. So du is going to be equal to 3x squared dx. So I want 1/3 of du because I only need to cancel out an x squared dx. All right. So we have what we need here to get rid of the u. We have what we need here to get rid of the x squared and the dx, but we haven't accounted for the bounds yet. All right. So what we need to do, because these are x bounds, I mean, it would kind of easy to gloss over this, but this is from x equals -2 to x equals 4. Well, my variable of integration now is going to be u. So I need to go from u equals something to u equals something else. So I'm going to evaluate my u equation for -2 and 4. So -2 cubed plus 8 is 0. That's an improvement. 4 cubed plus 8, 64 plus 8 is 72. That is not an improvement. So our new bounds are going to replace the old ones. So 0 to 72. Instead of x squared dx, I'm going to have a 1/3 du. And instead of x cubed plus 8 squared, I'm going to have a u squared. So I'm going to write it as 1/3 du. I'll put the u squared in here. And then we're kind of off to the races. The active integration should be very easy. Increase the exponent by 1, divide by the new exponent, 1/9 u cubed over the interval of 0 to 72. The benefit of doing it this way is that you don't have to reverse substitute. You don't have to put it back in terms of x because the whole thing's in terms of u, including the bounds. Now I could apply fundamental theorem straight away without having to worry about the x's anymore. The numbers are pretty large, so I have to account for that. So 1/9 times 72 cubed minus 0, so that's irrelevant. So we're talking about a pretty large number here, 41,472. All right. But like I said, no expectation that you do it by hand. You can pop it right into your calculator. You can also pop it into Desmos. For an online course, I don't want to be cheeky, as they say, but who says that? Some people. I heard it in a Harry Potter movie once. Yeah, but I don't want to minimize things and say, well, how am I going to know? But that really is the truth of it. Like, how would I know if you use Desmos or whatever? So whatever online source is short of cheating, do the work yourself, is going to be acceptable. All right, because it's kind of like I'll get you in other ways. So we don't want to get bogged down with the minutia. All right. So in the case of number 2, I would let u equal 4 plus x cubed, or x squared. Apologies. Du is going to be equal to 2x dx. I only need an x, so 1/2 du is going to be x dx. Got my nice highlight action going on here. So I can cross the T's and dot the lowercase j's. So I'll pop in the 2 and the 0. When I plug in a 2, I get an 8. Plug in a 0, I get a 4. Kind of was hoping for a 0. I like the 0 better, but it is what it is. So we'll be looking at an integral going from 4 to 8, 1/2, we got the du, and then u to the 1/3 power. Alright, so increase the exponent by 1, so u to the 4/3, divide by the new exponent, same as multiplying by 3/4, so 3/8 over the interval of 4 to 8. Alright, now if you're doing this by hand, the expectation or the hope is that you wouldn't be relying on the calculator to do the crunching for you, because if you did, then why wouldn't you just do math 9 from the beginning and call it a day? Alright, so you go as far as it makes sense to go in terms of substitutions, but 3/8, 8 to the 4/3, minus 3/8, 4 to the 4/3. So in this case, there's really not much to do with the 4 to the 4/3. I mean, I could try to kind of troubleshoot it a little bit. 4 raised to the 4th power is really 4 to the 3rd power multiplied by another 4. You know, so if you want to kind of expand this out a little bit, it's really 4, if I can get my pen to work, 4 to the 3rd power plus 1. Right, that's the same as 4 to the 4th, which you can break up and make it as 4 to the 3rd times 4 to the 1st, which would give you 4 to the 4th over a 3. So we're looking at 4 to the 3/3 times 4 to the 1/3. So that's 4 times the cube root of 4. So you're stuck with that cube root of 4. So there's, you know, there is a end of the road here. The 8 to the 4/3 is a little bit nicer, because you can actually take the cube root of 8, which is 2, to the 4th is 16. 16 times 3 is 48 over 8. Well, actually, I'll just kind of jump right to it there. 6 times 8 is 48, so 6 as a result. So 3/8 multiplied by 4 times the cube root of 4. 4 goes into 8 twice, so this would be the same as saying 6 minus 3/2 times the cube root of 4. Alright, so I mean, is it worth it to do all that? Probably not, you know, if I'm being completely honest. So let's double check and make sure I didn't screw that whole thing up. So I need the cube root, so math option 4 of 4. So you got that lovely looking number. All right, so let's get the original in there and take a look. So math 9, 0 to 2. We got the x. We got the cube root of 4 plus x squared dx. And there you go. All right, so we get an exact value, but it's a question of whether that was worth the effort. Depends, I guess, on the situation. All right, number 3. So it's pretty easy to see that, I think anyway, you know, if I'm being fair about it, when you're talking about power relations, it's pretty easy to see that the one that's got the higher power is probably the one that you want to go with in terms of defining your u. All right, maybe not in the first example that you ever do involving u substitution, but the more experience you get, the easier it becomes. All right, so let's go for it and see if it makes sense to let u equal x to the fourth minus 25. So du would be 4x to the third dx. Now, I only really need an x to the third dx, so let's get rid of that 4. So 1/4 du x to the third dx. All right, so we have our clean substitution there, so that's good news. On the bottom, we have that radical, but contained within that radical is that expression that we're going to replace with just a u. All right. The bounds, we got to account for the bounds. All right, so u of 2. So 2 to the fourth is 16 minus 25 is negative 9. U to the first, 1 to the fourth minus 25, so 1 minus 25, negative 24. These are hideous. All right, so let's see where this takes us. I'm going to get my pink highlighter involved. So 1/4 du over the square root of u over the interval of negative 24 to negative 9. All right. Now there is a school of thought that says, all right, well, maybe we should try to transform our expression so we can make our bounds a little nicer. You know, so if you're working with an expression that's going from negative 24 to negative 9, is there a universe where if we shift it over 24 units, the function, that we end up with cleaner bounds? Well, let's take the antiderivative first and see if that's even necessary. That line of thinking. So just rewriting a little bit, bringing the radical up, putting it in fraction form, or at least the exponent, increase the exponent by 1, u to the 1/2, divide by the new exponent, same as multiplying by 2. 2 times 1/4 is 1/2 over the interval of negative 24, negative 9. And it's at this point where I say, well, I'm glad I didn't put too much time and effort into transforming the function, because this is not going to have a solution, because I'm looking at negative bounds, and these must be outside the domain. All right, and that's something that, you know, in theory, probably should have picked up on way earlier. Didn't notice it, but I notice it now. If I try to put a negative into a radical, it's going to give me an imaginary number. All right, so I might have said undefined earlier. I meant to say imaginary. All right, but just going back here, my bounds, if I put a 1 in or a 2 in for x, it's going to give me a negative under a radical also. So there was never an instance in which this would give us a defined solution. So the bounds of integration were outside of the domain of the function, so how could it ever capture any area? All right, so number 4, that's the one you kind of, I'd say your eye probably focused on that one immediately once you turned to this page and said, whoa, we got a road ahead of us. But it's really not that bad, because anytime you involve exponential base e, the derivatives and antiderivatives are actually pretty clean. With u substitution, it's always going to be a challenge, or the challenge, to determine what the u is. All right, so you take a stab at it, and if it doesn't play out, you try something else, and if not, then maybe it's not a u substitution problem, right? But we have a bunch of different possible combinations of e to the x, 1 over e to the x, that we could put together. So it, you know, don't dilly-dally, just jump right in and pick something. Now, I kind of look at it and said, if I have a choice in the matter, what would I prefer to remove from this expression? Like, I mean, this would be great if it was just a numerator, if that denominator was gone. All right, so I can't make the denominator go away, but I can make that the u. and see where that takes me. I'm going to write it as e to the x minus e to the negative x, because when I anti-differentiate or differentiate, we're just best served to have it written in this form, just so we could apply our exponential u rules. So du would be e to the x, the derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x times the derivative of the exponent, which is going to be -1, multiplied by the negative in front of the e to the negative x is going to make it positive. All right. So having a look at that, and I'll just put the dx on at the end, having a look at that and comparing it to the integrand, I notice that this expression, it's kind of in a slightly different form, but this expression is the same as this. That's great. It's clean substitution. All right. Now, to some extent, I kind of got lucky. Now, okay, I want to be completely fair about this and transparent. Transparent first, but also fair. This is not my first time doing this problem, but if it was, I would have done the same thing. I would have looked at it and said, all right, well, what do I want to make go away? The denominator. Okay, how can I make it go away? Well, I'd like to make the whole thing go away, so let me try making that the u. Turns out our risk was rewarded here. But if that didn't work, maybe I would just let u equal e. Or maybe I'd let it equal the numerator, all right, and see where that takes me. All right, so, but this one fortunately worked out nicely. All right, so the numerator is going to get replaced with a u. I'm sorry, du. The denominator is going to get replaced with a u. So that smells like natural log in terms of an antiderivative, so that's good news. Got to take care of the bounds, though. So I'm going to find the u of the natural log of alpha. Now, what I could do, and I haven't really mentioned this until now, is we could work with this as a boundless expression. When we take the antiderivative, just leave it with vacant bounds and then reverse substitute it so that it goes back in terms of x, and then plug in the original x bounds. All right, so you could do it that way if you want. Sometimes it's more trouble than it's worth. Sometimes it's absolutely the way to go. So you're the best judge of that. All right, depends on the situation. So e to the ln, so this is me not doing that. I'm going to do it the way I've been doing it. All right, so e to the ln of alpha, minus e to the negative, again, x is going to be replaced with the natural log of alpha, so ln of alpha. So e to the ln of alpha is going to just be an alpha. So that's good. That's an old pre-calc rule. Now, for the second piece, and actually let me write the intermediate step before I go too crazy here. So e to the ln of alpha minus e exponent, the power becomes an exponent, power comes, geez, I don't even know what I'm saying half the time. The coefficient becomes the power. Power becomes a coefficient. It's the power rule for logs. All right, so I can rewrite this as ln of alpha to the negative first, which could also be written as ln of 1 over alpha. That's fine too. All right, the reason why I would consider writing it that way, and in this case definitely write it that way, is because I want to be able to apply the same rule, which is to say e to the ln of some argument results in the argument. All right, so e to the ln of alpha is alpha. E to the ln of alpha to the negative first is going to be alpha to the negative first. All right, so that's our upper bound. Our lower bound, negative ln of alpha, Now I'm actually gonna do that right off the bat here. I'm gonna write this as u of ln alpha to the negative first, so that when I make my substitution, it's a little bit cleaner. So e to the ln of alpha to the negative first minus e to the negative ln of alpha to the negative first. All right. So alpha to the negative first. Now these two negatives, whether you bring this down here or if you bring this up here, either way, they're going to combine to give us a positive. All right, so that's essentially just going to boil down to e to the ln of alpha, which is just alpha. So minus alpha. All right, so we're looking at the integral over the interval of alpha to the negative first minus alpha to alpha minus alpha to the negative first. All right. I'm going to shrink it down so it doesn't look as hideous. I want it to be smaller. Now let me try something here real quick. Yeah, it's just kind of like a quirky thing with the GoodNotes app. All right. Now du over u is really the same as saying 1 over u du. All right. So that in turn could be thought of as the natural log of u over the interval of, one to the other. So ln of u over the interval, and I'm just going to snag these two. So ln of alpha minus alpha to the negative first minus ln alpha to the negative first minus alpha. Now at this point, depending on what you needed to do the problem for, you might call it quits, you might continue on. All right. The only way you'd be able to continue on would be if you were to get a common denominator and go from there. So what I'll do is I'll just kind of box this as a final answer, but then just for giggles, let's continue on and see where this takes us. All right, so if you get a common denominator, we're looking at ln of alpha squared over alpha minus 1 over alpha minus ln of 1 over alpha minus alpha squared over alpha. All right. So then we could put them together. Well, we could put each individual pair of fractions together. Ln of alpha squared minus 1 over alpha minus ln 1 minus alpha squared over alpha. All right. Now, we could break apart with log rules. We could break apart quotients. Quotients become subtraction, but we could also go the other way. It's expanded out to subtraction, so we could bring it together and make it a quotient. All right, so we could write this as ln of alpha squared minus 2 over alpha
over or divided by 1 minus alpha squared over alpha.
Little keep change flip action, and we have a lot of interesting stuff about to happen here. All right, but we probably want to get a calculator involved and see what this answer ought to be, because this is actually going to clean up to the point of being like, whoa, I didn't see that coming. You know, that kind of level of cleanliness was sort of, or can be sort of unexpected, especially when you see something this messy. But I don't know why I hit copy. I meant to hit resize. But sometimes when you see something written in general terms, you start thinking, oh, well, it must clean up, otherwise why give it to us, you know, like why select the natural log, well, actually it wasn't natural log. Oh, actually it was, apologies, negative natural log of alpha to positive natural log of alpha. So ln of alpha squared minus 1 over alpha times alpha over 1 minus alpha squared. So these are opposite, exactly the same, so they'll cancel. These are opposites, so they'll cancel to a -1. The absolute value of a -1 is a +1. Oops, I don't need that anymore. Get out of here. So ln of 1 gives you a result equal to 0. All right, so I'm looking at this being like, whoa, that's entirely too clean for what we started off with. So let's take a look at our calculator and see if that's actually the case, or should be the case. So let's get it in there. I hit the wrong thing. Let me quit. Y equals, so alpha, y equals, I hit second y equals, brought up a stat plot. Second ln, bring in an x, plus 1 over, so alpha y equals 1 over e to the x. Same ingredients but with a minus sign. I hit second again. That time I just slipped. Alright, so looks like I got what I need. Let me take a look at the picture, zoom 6. Alright, so it looks like kind of like a rational function. Kind of makes sense. If I got a common denominator and cleaned it all up, I don't know that I necessarily would have predicted that it would look like this, but yeah, I mean, it's reasonable, I suppose. Now, negative ln of alpha to positive ln of alpha. All right, so forget about the fact that it's an ln. Actually, forget about the fact that it's an alpha. Look at it as you have the exact opposite value on the left from the right. All right, so it could very well be going from -2 to 2, or -5 to 5, or -1/2 to 1/2. And the fact that it's ln, all right, it's still another constant because it's taking the natural log of some constant alpha. All right, so it's just a question of whether or not it makes sense for it to be 0. Well, it does look like we have equal parts of area on the left as we do on the right, you know, below the axis, above the axis. So there's reason to believe, unless it's, you know, unless it's the kind of graph that appears to be symmetrical but isn't quite, we have every reason to believe that we're looking at something that's, you know, an odd function. All right, but what we can do is, we can't prove it. I mean, we did prove it, you know, but based off of what we just did in the solution to number 4. But if we want to verify it somewhat, what we can do is choose a couple of values for alpha and plug it in. All right, so that's what we'll do here. So I'm going to go second trace, and option 7. The lower limit, I'm going to make it negative ln of, I'll go 2. All right, it'll put the approximation in there, but it'll give me something anyway. The upper limit, ln of 2. So I'm letting alpha equal 2. It says error divide by 0, which I suppose makes sense because you're looking at an asymptote there at, well, where would it be, 0? Let me take a look at the graph. Yeah, and it looks like we have an asymptote at 0, so that's going to break it apart. I mean, we do have to learn about improper integration in order to be able to handle that. But what we could do is, instead of going from negative ln of 2 to positive ln of 2 in one shot, what we can do is negative ln of 2 to something really close to 0 on the low end. So negative 0.0001, for example. So that's giving me an approximation of the area contained between negative natural log of 2 and 0. So let's do that between positive 0.0001 and positive ln of 2 and see if it gives the same value. Yeah. I mean, if it's not exactly the same, it's only off by a smidge. It's not off by enough to cast doubt on the fact that they're opposite equivalent areas. All right. So that's that. Now, what we could also do is, again, prove is not the right word because we actually did the proof. We did it in general terms, so if we can verify it using Desmos. So I'll show you that real quick. In calculator, I type in the function. So just as y equals, and so I'll make a fraction, e raised to the x minus e to the negative x. So shift 6, so that brings up the caret, or the ability to type in an exponent, more or less. Oh, it's supposed to be plus. Well, you know what I could do? Quick copy paste job here. Before I make the change. So that's the graph. Now I can integrate. Like I said, over something like ln of 2 to ln of positive 2. And you know what, instead of calling it y, let me call it f of x, so I can refer to it in the integral rather than typing in the function again. All right, so it gives me a clean 0. All right, but then it begs the question, okay, well, what if it's not a 2? Well, let's make this an a. Now, if I slide my slider, it'll automatically create a slider. If you select, create slider. It'll give you undefined when the a values are negative or 0, which makes sense because natural log only exists for non-negative values. I'm sorry, positive values. But yeah, for all these positive values, it's giving you a result of 0. All right, so it's a nice little verification or demonstration.